this kind of thing. So, okay, let's start. Let's start with that. So, kind of with like foundation stuff, we had the ideas of like hybridization. We had the like shape and bond angles. We had resonance. Let's see if I can spell that. Let's see, resonance. Acidity, I guess we can say. What else do we have kind of at the start there? Just kind of conformations. We had all the different projections. So we had Sawhorse, Newman, and Fisher projections. We had isomerism. So we had constitutional isomers. We had stereoisomers. And within that we had enantiomers and diastereomers, as well as meso compounds. Let's see, I think that's most of the kind of like foundation topics.
Well, if I had to pick from those, I would say hybridization and
Okay,
acidity would be the
cool.
two that.
Okay, we can talk about those. All right. Let's just finish off with all the topics,
Sure.
and we'll then come back to those two. And Eileen, of course, if you have any that you'd like to go over as well, as much as we can in the time given, we can do that. So let's see. With like actual reactions, or let's see, we had nomenclature. So we had alkanes, alkenes, alkynes, alcohols, and then ethers. And I guess thiols too, but those are kind of boring. And I doubt you're going to have something on that. But technically that was covered. Let's see, we had reactions. We had SN1, E1, SN2, E2. We had radicals. So we had halogenation. With just halogens or NBS. We had all those fun alkene reactions, all those alkyne reactions, all the alcohol reactions, the ether reaction, singular. And then we had proton NMR, carbon NMR, and IR. And I think that's all the topics that we've covered. So all of this fun stuff. So I guess starting at nomenclature, is there anything else that was particularly troublesome?
NMR, but
NMR? Okay. I'm not sure how much we'll be able to cover on that, but we can
yeah,
do some. Was it, I assume, probably this one? Because carbon NMR is...
I guess I don't know. I feel like I have sort of a grasp on it now, but it was challenging.
Okay. Okay, so then we'll maybe do that last if we have time. Okay, and then it was just kind of the synthesis idea. Well, thankfully that's not really something that's covered on the ACS exam because it's multiple choice and, you know, you have about a minute and a half, so not really much you can do synthesis-wise.
Yeah, for sure.
So that's something more for, I guess, next semester. So we'll not worry about that right here. Okay, so let's talk about hybridization first. So cool. And again, Eileen, if you've got anything you'd like to go over, just let me know. So hybridization, remember, is our way of explaining why we have equivalent bonds in organic molecules. And what I mean by that is something like methane has 4 equivalent CH bonds. With the way that we think about atomic orbitals, carbon has 4 valence electrons, right? It's got 2s2, 2p2. But if we were to expect it that we were using these particular orbitals to make bonds in carbon, we would expect 2 different types. We would expect a bond made with an s orbital and a bond made with a p orbital, or rather 2 of each of those. So we would expect, you know, different bond lengths, different bond strengths, and various other things that we don't actually see. We see that with methane, every bond is identical. And so that tells us that we don't actually have these kind of discrete orbitals that we might think. And so we see that these actually hybridize in different ways, depending on how many bonds we're making. And it just depends how many electron domains you're going to have on your carbon of interest, or I guess atom of interest. So if something is sp3, it has 4 electron domains. Electron, let's try that again. Like methane, like water, those both have 4 electron domains. So those central atoms are sp3 hybridized. sp2 hybridized means you have 3 electron domains. Also with 4 electron domains, you have 109.5 degree bond angles. Roughly speaking, the more lone pairs you have, the smaller those angles get, but that's a minor consideration. With 3 electron domains, you have 120 degree bond angles. That would be something like this, or something like carbonate, where you've got 3 electron domains. That's an sp2 hybridized carbon. Another way to think about these things is sp3 carbons or sp3 atoms have only single bonds. With sp2 carbons, you have 1 double bond or a carbocation. Those are sp2 hybridized things. Alright, and then sp hybridization is when we only have 2 electron domains. That's going to give us angles of 180 degrees. And this can either be 2 double bonds or a triple bond. And so we have an example here. Carbon dioxide has 2 double bonds. The acetylene on the right has a triple bond. So both of these, this would be an sp carbon. These would be sp2 oxygens. because those oxygens have 3 domains, the carbon has 2 domains. With the acetylene, both carbons are sp. Hydrogens, of course, just have, they don't have any hybridization, they're just s. And so we can identify the atoms in all of these things. So this would be an sp2, these would be sp3, these fluorines on the side, because they've got 3 lone pairs. This would be sp3, sp3, sp2, sp2. So along all of these things, we can just look at all of the atoms and see how many domains they have, how many things they're bonded to. So quick and dirty way is just look at how many double bonds you've got on the atom you're looking at. And this will also tell you the shape, right? Something that's sp3 will be tetrahedral. Which gives you bond angles of roughly 109.5. Again, that can be slightly varied, depending. sp2 gives you trigonal planar. And that's going to be... So TACO is... let me see if I can do this. Maybe that'll help. Okay. So that'll be 120-degree angles. And then for SP, those are linear things with 180-degree bond angles. So hopefully just a quick little review here to help you identify the hybridization of a particular atom. So if we just take a look at some of these things, I don't know. Here's one. If we want to identify the hybridization of all of these atoms, we can do that. So, of course, we're going to want to put in our lone pairs to make sure that we get all of the electron domains there, just so we make sure. And if we really want, we can put in hydrogens as well, just so we are, once again, aware of how many bonds these things are making. So, that oxygen up there should be sp2, right? Because it has 3 domains. We could also say it has a double bond. Either way you look at it, that'll give you sp2. This carbon that it's bound to is also sp2, because again, it's part of a double bond. Otherwise, it's got 3 domains. It's got the oxygen, it's got the carbon on the left, carbon on the right. That's 3 total domains, and so we're going to end up with sp2 there. So, okay, let's take a look at the next one. This one should also be sp2 because it is bound, it's got 1 double bond. We could also think it's got the hydrogen, it's got the carbon that has the oxygen, and it has the carbon below it, so that's 3 total things. So 3 domains, or 1 double bond is sp2. We get sp2 on these, and then everything else is sp3. All the ones that are just single bonded are sp3. Alright, and if you wanted to prove that to yourself, you could have the hydrogens drawn in. That may help.
Sweet.
Go ahead.
Oh, I just said, that sounds good. I like your quick and dirty.
Oh, okay. I thought I said wait. So, okay, cool. Great. So, yep. Quick, very fast way of doing hybridization. Okay. Acidity. Okay, this is little bit longer, but we're good because this will talk about stability of various things. So, the other two of you, any questions on the hybridization? We just did a quick little recap of that. All right. Well, let me know. Acidity. So, acidity, we have our comparisons to make. C stands for cationic. We'll take a look at all of these things. A refers to the atom identity. R for resonance. I for induction. And then O for orbital. So this is the order that we look in these things. Again, this is a general order of predicting the stability of an acid. One thing to note, the cationic actually refers to the acid itself. And all of these other ones refer to the conjugate base. And the conjugate base is what's left over after you remove the proton. So we want to look at the stability of a negative charge on all of those ario parts. So cationic acids will always be more acidic than their counterparts would be. So for example, the cationic form is always more acidic. Always, always, always. Often by, a trillion times more acidic, like huge values more. So cationic acids are always much more acidic. So, and all of these things, it's always going to be an apples to apples comparison. So, it's hard to say if you have OH versus NH3+. Like, that's not a fair comparison. Because the NH3+ is positive, but these actually have pretty equal pKa's. So they're pretty equally acidic. So this is not something that we would be able to compare. We're comparing directly things that are, the only difference is that one is cationic, meaning it has an extra proton, versus the other one. And so the extra proton makes it much more acidic. So always, this is all about comparing apples to apples. Okay, meaning similar things. All right, so when we talk about the atom identity, we're looking at the conjugate base of the acid. So if we're comparing we can take a look at their conjugate bases. So the conjugate base for all these things, we would remove the proton, and now we have a negative charge on these atoms. We want to think which one of these, or what's the kind of stability here of all these things. So for negative charge stability, the biggest factor is size of the atom. So anything that's in a lower period, meaning farther down on the periodic table, will be more stable with a negative charge. It can hold on to that negative charge much better than something smaller. So we want to look at the row of the periodic table. So a lower period is always going to be more stable than a higher period atom. So if we compare these, the oxygen is in period 2, sulfur is in period 3, nitrogen is in period 2, on the periodic table. So sulfur wins. That is always our first consideration because it's the most important one. So, great. After that, for things in the same period, and this is our second consideration here, so we're not going to worry about this if all we have are different periods of atoms, just go with period. After that, for things within the same period, that's when we have our second consideration, which is electronegativity. And for this trend, more stable is going to be the more electronegative atom. So first thing we deal with is size, then we deal with electronegativity. So looking at these three, this is going to be our number one pick because it's in period 3. It wins right off the bat. That's our most acidic. Or we can say it's the most stable conjugate base. Remember, those two things mean the same thing. So that's saying that this thing is the most acidic. Or we can say this is the most stable conjugate base. Or we can say, again, the acid form of that was the most acidic. Those two statements are intertwined. Most acidic compound gives you the most stable conjugate base, or vice versa. So, now that we have our size part out of the way, we have chosen our biggest atom, which has the lowest period. I think I wrote those words badly. I chose bad word choice there. I meant lower on the periodic table, but the number of the period is higher. So, what's the better way to write that? Let's see. Let's edit this.
Closer to the bottom.
Yeah, lower on the periodic table. There we go. And then higher on the periodic table. There we go. Whatever. Closer to the bottom, right. So whatever's lower on the periodic table is bigger, right? More shells, bigger atom. So now we're looking at electronegativity. Now that we have everything in the same period, we're only comparing now our oxygen one versus the nitrogen one. Oxygen, as we know, is more electronegative than nitrogen is. So this will be our second most acidic. And then that means that this was the least acidic. So that was our least acidic one. So that is atom identity. And again, notice these are all comparisons of relatively equal. They're very similar, right? The only thing that's different was the atom identity here. So we're able to make these determinations. So, of course, if I threw a cationic acid at you, it's a lot harder to compare because that's no longer a fair comparison to make. So, cool. So, questions on atom identity. So, first consideration, size, where it is on the periodic table. Second consideration is electronegativity. Always in that order. Okay.
Got it.
Cool. Next one is resonance. We want to just remember our resonance things here. We want to... what's the best way to describe this? Things with p orbitals can resonate. And then those are typically resonating We can resonate positive or negative charges with double bonds. That's what resonance means for us. So, for example, if we have something like this, we can compare these. If we take a look at their conjugate bases, so all of these, the atom identity is the same, right? They're all on oxygens, so and none of them are cationic, so we have those first two out of the way. So now we're looking at resonance. So we're going to take a look at the conjugate bases again. And so now all of these have got their negative charge. Again, since all of them are on oxygens, the atom identity is the same, so we get no benefit there. So now we have to consider if these things can resonate. Right off the bat, we should be able to identify that this thing cannot do resonance. There are no double bonds nearby it. So even if there's a double bond down here, it doesn't matter. It's got to be right next to it in order for it to resonate. So we have no resonance with that one. It automatically will therefore be our least acidic. Remember, the better resonance you have, the more stable your conjugate base is. The more stable your conjugate base is, the stronger your acid is. So this one has no resonance in the middle, so therefore it's the least acidic. And remember, you've got to have a double bond right next to it in order to resonate. So if we do want to resonate, we can do that. We can resonate both of these things. Notice we always start our resonance arrows at a lone pair, or a double bond. We could start it there, but generally speaking, we usually start at lone pairs. And so we can draw the corresponding resonance forms of these. Don't forget, a resonance arrow is double-headed. So if we do this, we end up with a lone pair on that carbon. Whoops. With this one, we end up with a lone pair on oxygen. So which one of these is better? Resonance forms, that is.
I'd say the one on the right.
The one on the right, exactly. The reason for that is because now we're looking at atom identity of the resonance. So we were able to resonate it to an atom that is electronegative, so that's a good thing. With the one on the left, we've resonated it to a carbon. Carbon is not electronegative, so this is actually a minor contributor, right? This is going to be not very significant because it's not more stable. So this one would be our major one. And these two would be, since they're effectively equivalent to each other, we could just rotate that bond if we were so interested. They're both major contributors because we have equal stability between the two. So we're able to effectively disperse that negative charge throughout two atoms instead of one. Whereas with the one on the left, resonating to a carbon is not as good. So it's not going to spend much time as the negatively charged carbon. So it doesn't resonate very much. So it's got a kind of weaker resonance. So it's going to be less stable than this one. This has better resonance. In fact, it's got the best resonance of these three, and so it's going to be the strongest acid. So that's the most acidic, and then of course then the one on the left will be our in the middle compound. So if you can resonate, you will beat out ones that can't for apples to apples comparisons. So if you can resonate, you're a stronger acid. If multiple of your choices can resonate, you choose the best resonance. The best resonance will kind of also follow the REO rules, right? We want to minimize formal charges. We want to, if we have negative charges, give them to the most electronegative thing. If we have positives, give them to the least electronegative thing. We want to avoid having incomplete octets. So we don't want anything to have only 6 electrons, so carbocations are to be avoided. And so we just want to keep all these things in consideration. All right, so resonance is its own big topic, right? So you can review that. Next is induction. These effects become less and less important, but induction is the presence of nearby electron withdrawing groups. Like halogens, like nitro, like sulfonyl. These are electron withdrawing groups. Nitrile. These are things that can inductively withdraw electron density. Carbonyls. Those are also electron withdrawing groups. So, for example, if we compare these acids, that's supposed to be an F on that side. So the more electron withdrawing groups you have nearby your negative charge, with that, we're just looking at how many we have got. So with the one on the left, we have 3 fluorines. The middle one, we have a single fluorine. And then the one on the right, we have no fluorines. So the one with the most will be the most acidic, because all of those fluorines are going to be withdrawing electron density. They're going to make this slightly positive, which is going to help stabilize the negative charge that's resonating between the oxygens there.
So you drawing that iodine actually made me think of a question.
Yeah.
If you were comparing something with a fluorine versus an iodine, I know fluorine is more electronegative, but iodine is way bigger.
Indeed. So, but that doesn't matter for here because the iodine is not what the H is attached to.
Oh, right. Okay.
Since the halogens in this case are attached to a carbon, this one will be a weaker dipole than this one will be. So with the electron withdrawing groups for the halogens, fluorine will be better than chlorine, will be better than bromine, will be better than iodine. So for their ability to withdraw electron density.
Got it.
Yep. And so just the more you have, the better. You know, I'm not going to be able to do something like, well, compare this with this, because that's just unfair, right? Is 1 fluorine better than 2 chlorines? I have no idea. So not a fair comparison there. So it would either be just multiple of them, or a comparison of their own strength, or just the lack thereof. So this one would be the best, followed by this one, so most acidic. This one's in the middle, and this one's the least acidic. And then we're not going to really worry about all these things. The iodide one would be in between these two, right? It would be in between the one with the fluorine and the one that did not have anything at all.
Gotcha.
Right.
Cool.
So, yeah. Okay, so that was, and what else do we have with acids? Orbitals. Something on an sp orbital is better than sp2 is better than sp3. Really, we only ever talk about this with acetylene. That proton is much more acidic than a vinyl proton would be. Simply because the orbital, because this is 180 degrees, it's got the room to exist and nothing's in its way. With a vinyl one, you have, let's make it super big. You have these kind of repulsion here, where that you don't have with the sp hybridized carbon. So this is just a minor thing, but an sp carbon will always be more acidic than an sp2 carbon, which will always be more acidic than the equivalent sp3 carbon. Simply because you have the room for that lone pair to spread out. Because things are 180 degrees, they're already far apart from each other, and so you're able to accommodate that a little bit more. But again, it's not likely that you're going to just end up with just these. But we already know that the triple bonded carbon, that's the only one that we even consider acidic. And we use it to add alkynes to compounds, right? We can use sodium amide to attack things.
That actually reminds me of the exam we just took.
Mm-hmm.
One of the questions on there for I don't know if you want to look at that, but
yeah, let's look at it. I don't think I've even put the key. Okay, let me I've got to download it. So let me open Discord here and just send myself the exam so I can have that, and then we can look at that. So
that was like the only question that I had no idea how to do.
Great. Well, I mean, kind of great, I guess. Okay, so all right, that's sending to myself. Okay. Let's open Discord here. Grab that. Okay, I've got my fake channel for where I have all my files. Okay, I'm gonna open this. Maybe. Okay, so let's take a look at this. I'm gonna move this vertically. No, I won't. Okay, which one did you say? 4?
4A.
4A. 4A. Ah, okay. So, yes. So, in order to add carbons to things, we have two options, right? We can either use a Grignard or we can use an acetylide. So, in this case, since we already have something that has the triple bond, it doesn't really make sense to use a Grignard here. So, we just want to consider what's different between the starting material and the products. And so, we want to think how many...
ethanol.
Yeah, we've added 2 more carbons. And we also have this... We've added an OH to this molecule. So, we know that we can deprotonate this thing, make it into the acetylide. I'm actually going to just move back to this because I think I can have the room to do this. So, and we're going to, okay. So with this thing, we're adding 2 carbons and we have an alcohol that's produced. And so we just have to think, we know that we're going to be using this acetylide as our nucleophile. Our nucleophile is the one that has the negative charge. It's the one that's going to be attacking our electrophile. Electrophiles generally have either a partial positive or a full positive. So we're going to try and find the appropriate electrophile. And so when we think of something that's producing an alcohol that came from an electrophile, that generally speaks to an aldehyde or a ketone. Because when these things get attacked, if a nucleophile attacks them, they open up and they form an alkoxide, and using water or an acid wash will restore the alcohol. And so we have to think, if this was a ketone, we would have a second carbon there. But in this case, it's a hydrogen, because this was an aldehyde to start. So we want to look at what we're making here. It looks like this. We have a hydrogen on this, because this is a secondary alcohol. A secondary alcohol means that this must have come from an aldehyde then. So that means our aldehyde of choice has 2 carbons, and it's an aldehyde. So we in fact have, our first step will be the aldehyde. We can put the H if we want. And our actually, I think since we're starting at the alkyne itself, we want to make this into the acetylide. So we're going to use our nice strong base, turn it into the acetylide. Then we're going to put in our electrophile. And then the last step for adding to a carbonyl is we need to do an acid wash at the end, just to make sure that we've protonated our, we've got a protonated form of our alcohol at the end.
It's just that simple.
Yep.
I think my brain was not working after like 4 hours.
And that's normal. So, because again, there's a lot to think of with these sort of things. So yeah, it's simply a matter of looking at your product and saying, okay, well, we've got a secondary alcohol. We have quite a few ways to make those, right? We can have a bromide there that we're going to replace. We can have a carbonyl that we're going to reduce, or we can just make the alcohol by attacking a carbonyl compound. And it's simply a matter of, I mean, I can't say simply, but kind of simply, a matter of figuring out what the best way to do this would be.
Yeah.
So, so in that case, first thing, make it into the nucleophile, then you throw in your electrophile, and then just make sure everything's got a nice proton at the end. Okay, were there any others on the exam you would like to go over? I'll put the key up later today as well once I decide to write that. And again, anyone else here, if y'all have questions, like, just speak up.
I don't have questions on the exam, but I was wondering if we could go over SN1 reactions.
Sure. Yeah. Okay, let's do it. So, Shane, think of other questions. In the meantime, we'll talk about SN1 reactions. So, SN1 or solvolysis reactions. So, let's maybe start by first looking at the reaction conditions that would lead to SN1, like kind of the ideal situation. Ideally, your substrate, which would be your alkyl halide, would be tertiary or secondary. You cannot really do this with primary unless you have places to migrate your carbocation. But so tertiary is the best, then secondary, and primary is very hard to make happen unless you happen to have a lot of migration possible. So your nucleophile is the same as your solvent, which is a polar protic solvent. Polar protic solvents include water, methanol, ethanol, isopropanol. Generally speaking, it's just all manner of alcohols. Those would be your examples of polar protic solvents. And it's the same as your nucleophile. So it's going to be what's substituting your alkyl halide will be your solvent. And your solvent must be polar and protic. Protic means it has an acidic hydrogen on it. So if we want to take a look at these things, and then we also typically want low temperatures with this, because if we put heat, we run the chance of doing eliminations instead. And then the last thing we need to know about these is that the mechanism has a carbocation. So we just need to be aware of potential rearrangements that may happen because carbocations mess everything up. So something that would be a classic example, here's a tertiary alkyl halide. If we put this with methanol, we will end up substituting our alkyl halide with our solvent, right? Technically, the first step for this, we lose our halogen, so we lose a chloride. We end up with a carbocation. That carbocation will be attacked by your nucleophile, which is your solvent. So that's going to come in and attach itself onto your carbocation. We are left with something cationic, which means we can have a base come in, maybe another methanol molecule can come around, or we can use the chloride. Either of them would be similar, and we just need to deprotonate that. And that will give us our product, and we will have as a byproduct a protonated methanol. And so that's what we end up getting here. So the hardest part about SN1 reactions is the fact that we have the carbocation there. As we know, carbocations destroy compounds. They will do whatever they can to rearrange. And so that's the hard part, is predicting when you're going to have a rearrangement. And we can take a look at those. So when do carbocations rearrange? There are three ways of rearranging, right? We have the hydride shift. We've got the methyl shift. And then we have the ring expansion. And if we want to think about when a hydride shift occurs, that's when you have a primary or secondary carbocation next to a tertiary carbon. So for example, if you have a secondary carbocation that is adjacent to a tertiary carbocation, you will get a hydride shift happening there. Let me move these down just so we have more room here. So what's going to happen is, because the carbocation will want to stabilize itself, it will move a hydrogen over. And in doing so, we will now have our blue hydrogen on the carbon that used to have the carbocation, and now we have our positive charge on the tertiary carbon. And that's the best situation, right? Because of hyperconjugation. You can also see hydride shifts happening if you have a primary carbocation next to a secondary one. So if you have a primary carbocation, you can move that to a secondary carbon. You always want to go up. So primary can go to secondary, primary can go to tertiary, secondary can go to tertiary. So always you're moving up in your substitution on the carbon. So the more you can increase that, the better. So this would hydride shift to give us the secondary carbocation. So we always want to be able to make it as stable as possible. All right, so those are the conditions that you can get a hydride shift. All right, a methyl shift will occur when you have a primary or secondary carbocation next to a quaternary carbon. So, with this, examples of this would be when you have a secondary carbocation next to a quaternary carbon. So this would be prime conditions for a methyl shift to happen. So one of our methyl groups, does not matter which one, will move over. So now we have a methyl group on this carbon, and we still have two methyl groups on that, if I were to number these, on that, what we've labeled carbon 3. It now is a tertiary carbocation, and so we have stabilized it. So that's when methyl shifts happen. And of course, if you have a primary one next to a quaternary one, you can have this happen as well. So an example of that, if we had this carbocation, we could move this methyl group over. And so now we have 1, 2, 3, 4, 5. And we now have our carbocation here on the tertiary carbon. So this would be shifting from a primary. We're going to do a methyl shift from that quaternary carbon over here. All right, so those are the conditions for a methyl shift. So hydride shift, things are next to tertiary carbons, or if you're primary, you're next to secondary. Either way, you're increasing. Methyl shift, you have to be next to a quaternary carbon. So a carbon that has 4 carbons attached to it. Ring expansions are less common. These are more something we use for mechanisms rather than for actually predicting the products. But they happen if a carbocation is adjacent to a a non-6-membered ring. So you can have a 5-member ring, 4-member ring, 3-member ring. Those typically can expand with these. So an example of this would be something like this. We're going to expand our ring. Notice we have the carbons that's used to be there. That bond is now going to be moving. We're going to expand this to now a cyclobutane. And if we pretend that this one had a methyl group on it, just for fun, we would end up with that carbocation there. Why do we know it's there? Because, here, let's make these different colors. The electron, the bond here is breaking, right? We can break it in either way. We can pretend that that bond is now negative here and positive there, and then we can just connect to a negative and a positive. We can think of that as a homolytic cleavage, kind of. But the point is, it can go on either side. It doesn't matter, necessarily. Oh gosh, let me fix the blue. So we're going to end up expanding our ring. Our blue carbon is here. Our purple carbon is the one that's going to end up with the positive charge. And then the carbon in between them is where our carbocation used to be. Used to be right there. And of course, now that we have a secondary next to a tertiary, it would move over. It wouldn't expand because the carbocation is now on the ring. Expansions only happen if your carbocation is adjacent to the ring, meaning it's 1 carbon away, 2 carbons away, whatever it may be. It's got to be nearby a ring that's small. Because you also have ring strain as a driving force to make this happen. So if you have a 6-membered ring already, there's no reason to expand it. It would just do a hydride shift or something like that to try and stabilize itself. So it's really only for non-6-membered rings. And so, yeah, we would do a hydride shift after this, and we would end up with our carbocation now down there. Because we have a secondary next to a tertiary. So you can definitely have multiple things happening at once here. And it's not to say that the ring expansion always happens. You could definitely also just do a hydride shift instead. And instead end up with your carbocation here. They'll both happen. Carbocations suck. They ruin everything. So you could instead have a hydride shift happening. So just be aware of that. So it'll be obvious if there's a ring expansion happening, because you'll see that I started with a 3-membered ring, now I have a 4-membered ring. Gotta have expanded that somehow, right? So it's not something that's easily predictable, but when it happens, it's easily identifiable, if that makes sense. Ring expansions are really the only way to end up with a bigger ring than when you started with. So you start with 4, you end up with 6, that's a ring expansion. Start with 3, end up with 5, ring expansion. Start with 3, end up with 4, ring expansion. Start with 4, end up with 3, I have no idea, because that's very unlikely to happen. So yes. Alright, so just be aware of all these things with SN1 reactions. So if we were to take, say, let's just do one more. If we were to give this an SN1 treatment, we know that we're going to kick out the bromine. That's always the first step. So we have our carbocation. So with this carbocation, we have to now check, do we have conditions for rearrangement? Do we have a primary or secondary carbon next to a tertiary carbon, or the second case? Or do we have one of these next to a quaternary carbon? We see indeed we have a secondary next to tertiary, which tells us we're going to have a hydride shift happen. So this hydride will move over. We now have our carbocation in its most stable position. At this point, our water comes in, attacks the carbon, and we're going to have another water molecule come around and grab that proton. Oops. And so we're going to end up with an alcohol here on our tertiary carbon. Alright, so the hard part about these SN1 and E1 reactions is just the migration of the carbocations, because they will rearrange your molecules. Okay, any questions on that? Does that help, Eileen? Even a little bit, I hope.
Oh yeah. Oh yeah. It actually helps a lot. It helps to follow along with you.
Good. All right, I've got about 10 more minutes. If you guys would like to go over something else. Shane, did you happen to maybe find a problem on the exam that you wanted?
Really.
Okay.
Not really.
Is there anything else, Eileen, of this lovely list of thousands of topics that you'd like to also go over?
I feel like I had a lot of questions, but my brain just blanked. I forgot. But do you think we can do something where we go from one projection to another and like a rotation happens, or we have to have the diagram or something?
So why don't we take this butanol we just made? It's totally not a butanol. It's totally got more than 4 carbons. Anyways, we'll pretend. It's methylbutanol, right? Let's go ahead and take this into a Newman, and I guess it doesn't really matter because this is not chiral. Here, we'll make it chiral. Poof. And we'll make the hydrogen have the dash there. So let's go ahead and do a Newman on this thing. So if we want, let's look around those that bond there. So that's going to tell us that our front carbon has got a methyl group pointing down. And then since all we have otherwise is hydrogens, we can just put those in. The back carbon has going up, it's got a methyl group. Going on the wedge is the right side. So the wedge here is the OH, and then the dash is the hydrogen. So that would be our Newman projection. So just remember that like you kind of want to rotate your head or your molecule so that we see that this thing is pointing down. This one points up. And then remember that wedge is the right side, and then dash is the left side. So since our hydrogens technically are on both wedge and dash here, doesn't matter, but on that front carbon. So that's what we're looking at here. So cool. If we want to rotate this, let's see, what should we say? Let's rotate the front carbon 60 degrees counterclockwise. Now I gotta think which way is counterclockwise. That's to the left. Okay, so this thing is gonna be moving counterclockwise. 60 degrees means we're going from staggered to eclipsed. 120 degrees means if we're staggered, we're staying staggered, or if we're eclipsed, we're staying eclipsed. And then 180 would be just completely switching it around, right? So we're going to be now moving from staggered to eclipsed. So our back carbon we're going to keep the same, right? That's all going to stay the way it was. And then the front carbon, everything is moving 60 degrees counterclockwise. So that methyl group that was pointing down is now going to be pointing to the right and also down. So we can draw that like so. So now it's going to be overlapping that OH. And so we want to look at the next one. We have a hydrogen pointing to the right up. It's now going to be pointing straight up. So that hydrogen is now pointing straight up. And then the hydrogen that was top left is now going to be bottom left as we move these things around. And so we will now have this thing eclipsed. Because now we have the groups overlapping each other. This one right here was staggered because they are not overlapping. And in fact, because our bulkiest groups are the methyls, they are on opposite sides. That means this is anti-staggered, which is the best, the least energy conformation, because there's the least amount of overlap happening here. And we can, I don't know what we'd like to do with this. We can rotate it another 60 degrees. We'll rotate that front carbon again 60 degrees, counterclockwise. 60 degrees means we're going from eclipsed to some sort of staggered conformation. Remember, 120 degrees means you're doing the same type of thing. 60 degrees means you're switching between eclipsed and staggered. Alright, let's do it. So back carbon stays the same. Oops. Front carbon, now we're going to move. Our methyl group that's pointing bottom right is now going to be pointing top right. Oops. Our hydrogen that was pointing up is now going to point top left. The bottom left hydrogen is now going to be pointing down as we rotate this front carbon again 60 degrees. And so we want to analyze it and think, okay, well, we have our bulkiest groups kind of next to each other. And we have a special word for that, right? Do you remember what that special word was?
No.
Shindy, you remember?
I can't. I was trying to remember. I was trying to remember.
It is sterically hindered, and its special term is called gauche. Because we have these minor interactions. It's still kind of staggered, but it's got these what are called gauche interactions because we have minor overlap between them. So the word here is gauche. And then if we just rotate one more time, we're going to end up, just in the interest of time, I'm just going to draw it We're going to have our methyl groups right on top of each other. And then, oops, these should be towards the middle. That H is ugly. What else do we have here? Just 2 H's, okay. This one now, we have the methyls right on top of each other. That's the worst we can have it, and this is called syn eclipsed. So regular eclipsed is when we have overlap, but that's not the worst overlap we could have. Having your bulkiest groups touch each other, that's the syn eclipsed. So the methyl groups are our bulkiest ones here. So those are going to be the ones that are bonking each other. And so we would call this conformation syn eclipsed. This one here where they're adjacent but not overlapping, that's gauche. And when they're the opposite sides, that's anti-staggered. All right, so just here, I'll move this up so we can see all of it. Alrighty, so those are, and I guess we just have regular eclipse too. So we have all these different fun words we can think of for it. So, hooray! All right, so yeah, go ahead.
If you were gonna
go from Newman to
to Fisher projection, would you
through
go
Sawhorse or something first?
Through Sawhorse
Not
or
necessarily.
something first?
You'd want to do it such that you have two things pointing down. So if we take, I'm just going to take a random Newman projection if that's okay.
Sure.
And then we have, I don't know, how about an H there and a fluorine behind it. We choose one of these to be the top, one of them to be the bottom. So we can say the methyl group is going to be on top and the butyl is going to be on bottom. It does not matter which one you choose. Actually, it's going to be easier to do the other way. Let's do this way. So if we put the butyl group on top, that's actually going to be the easiest for us. We're going to have our methyl group on the bottom. And we're going to see that we have on the right side, on the back carbon, the carbon that has the butyl, that's got a chlorine. On the front carbon on the right side, we have the OH. On the left side of the front carbon, the one with the methyl, we're going to have a hydrogen, and then the one in the back, we have fluorine. So it's easy when you have two things on the bottom. You could go through Sawhorse first, not a problem, but going from Newman to Fisher is not terrible. Easiest is when you have your front carbon on the bottom, your back carbon on the top, because that way everything will be exactly the same. If we wanted to do it the other way, we would end up just flipping everything. But it'll work either way. So these were on the right. Notice in our Newman, and they stay on the right. These are on the left, and they stayed on the left. And the only thing is we want to choose one to be on the bottom and one to be on the top. Generally speaking, it's easiest if your front carbon is on the bottom and your top carbon is the back one. All right.
And if you went to,
and then if you went to the Sawhorse from the Fisher, you would just swap the fluorine and the chlorine essentially.
Depends, because you could have a Sawhorse that is staggered. You could totally have.
Right.
And then if you need to rotate it, yeah, then you would rotate it. And so yeah, if you need the butyl up, then yes, you would flip the fluorine and chlorine if you wanted to rotate that one. If you wanted to rotate this 180 degrees, so that you end up with a true Sawhorse, which should be staggered, you're going to end up with butyl up. You'll have the fluorine now there and the chlorine be on the other side. So, yes, you can interconvert that way.
All right.
Alrighty.
All right.
So, if questions come up as you are studying, go right ahead, put them in chat. I will try and answer them as best I can in words or pictures. But other than that,
I just had a question about
I guess I just had a
yeah.
question about the final.
Multiple choice.
Yeah.
So multiple choice.
70.
I forget how many questions you said it was.
Yeah.
70.
Would you say subjectively?
Would you say subjectively the questions are going to be easier because you have less?
So if you
time
take
on
a look
okay.
at the practice exam, you'll see the difficulty of the questions. You can open it now if you want. You can take it as many times as you want. So, so if you just take a look at it, you'll see that. Let me open it too. I can actually. If you take the quiz, you'll see the questions are pretty reasonable. And so I tried to choose ones that would give you an array of the types of questions that are going to happen, so you can see just a variety. So you'll have some kind of conceptual ones, some just type of mechanisms, some predict the products. So you're looking at about 1.5 minutes each. Some will be really fast, of course, and some will take a little longer, but on average you're looking for 1.5 minutes each. Alright?
Okay.
Cool.
Okay.
Alrighty, so I will